Hello everyone, I hope you're all enjoying your quarantine. Recently I've been thinking a lot about image segmentation. Now it has a lot of really cool applications, and what I wanted to do today was just implement a really simple program or algorithm in Python so we can actually understand what the most basic form of image segmentation is, because from that point on we can start expanding our knowledge. So we're going to just start with a simple, basically like a binary image segmentation. We're going to look at images that have two objects and we're going to try and separate them as much as possible. But before we do that, let's just have a quick Google of image segmentation so we actually know what we're doing. So I've already Googled it, but if we look at some Google images and we type in image segmentation, we get a bunch of these pictures. Now image segmentation can actually be split further into two categories. We can do semantic segmentation and we can just do instance segmentation. Now if we actually look at this picture here, it's a really good image. This is a perfect example of semantic segmentation. We've got a legend on the left hand side here, and it says every person has this dark blue color. We can see that. Every car has this dark red kind of color, which we can see in the background, and roads are purple, which we can see up here. And our vegetation, our trees and stuff are this green. So the point being, in semantic segmentation, every object of the same category will have the same representation. Now this is really useful because then you can kind of build a rule for, anything which is blue is a person, anything which is green is a tree, blah blah blah. So in instance segmentation, however, we treat every object as its own instance. So even though these two, this is a person, and 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 so on, you can see they've all got their own unique color representations. The same goes for these cars. So this is an example of instance segmentation. Now they're both really important concepts, especially in self-driving vehicles. You can actually check out my blog post which I wrote about how Tesla uses image segmentation. It should be the first link in the description. Anyway, so that's what image segmentation is. Now this is all a bit more advanced. We can see all these colors. We're not going to be doing that today. We're just going to be dealing with basically this binary image segmentation using OpenCV. So we all understand now that in image segmentation, all we're trying to do is determine what pixel belongs to what object in that image. So before writing some code, I'm just going to quickly go into my resources folder, which is just where we're keeping some images, and then we can just look at them quickly. I'm going to start with this coins.jpg. We should probably talk about a couple of things. So this is exactly what you expected. It's just a couple of coins. We've got a white background and then two coppery coins in the foreground. But what's interesting to note, and a problem we won't be able to solve today with our binary classification really, is that if you look closely, there are parts of the coin which have kind of deteriorated, or you can even think of it as glare, like of sunlight glare and stuff like that, where it's shiny. Where this looks closer to this white background than it does to this coppery color, especially when we're going to do this binary segmentation. So that's one of the images we're going to be working with. The other image we've got is this blend, which is quite interesting, where we kind of blend from pink into this turquoise color. And it's going to be really interesting to actually do this with binary image segmentation. And then the last one, which is kind of actually a bit trivial, and I might actually exclude, I haven't decided yet, is this colors.jpg. So those are the three images we're going to be working with. So now we can actually start writing some code. So this is the moment we've all been waiting for. We're going to write some code now. I created this empty Python file called seg.py. And I've actually been using Sublime recently, so I'm going to open, because I've been doing a bit of web development, and Sublime is much better for web development than Emacs. Emacs is just a text editor for like scripts and stuff generally. That's what I use it for, at least. You probably don't care. That's right. So we're going to import two things for now, and we're going to import OpenCV2, which is actually just CV2, and we're also going to from matplotlib. We're going to import pyplot, which we're going to use to display our images, and we're just going to import that as plt. don't think we need NumPy or anything right now, but if we do, we can just import it later. So of course the first thing we need to do is we need to grab our image. Luckily CV2 gives us a method for this. We can just say imread, and then we just need to give our file path. So we're going to say resources, and we're going to get our coins.jpg. Now, we've said already that we're not going to be doing like any crazy image segmentation. We're going to be doing what's kind of like just binary image segmentation, but we're also going to play around with a couple of different methods for it too, so definitely stick around. But what we want is we want grayscale values, right? So we're going to have this color array where every pixel has 3 values: a red value, a green value, and a blue value, our RGB values. And we want to convert that to grayscale, so we just have one value. So it's going to give us a brightness value where 255 is white and 0 is black. So let's define grey, and we can do that again with another what's this, CVT color, I think, another CV2 method. And we're just going to pass our image in here, and then we've got another CV2 method which is actually color, and then we're going to convert it from, well, usually we would say RGB, but actually in CV2 they use BGR, and we're going to convert that to grey. Now I'm actually going to define something quickly also, because we want to show our normal image too in matplotlib. So just stick around me here for a second, and we're going to say image color, and what we're going to do is we're just going to grab all of this, but rather than converting it to grayscale, we're going to convert it to RGB. And the reason for this is that in matplotlib they still use the RGB. So right now if we tried to display the image, we would actually be giving it BGR values, so all of our colors would be completely mixed up, even though it would still work. So now we've got our original image. This is this is our original image, and then this is our grayscale image. So I think what we should do now is just plot it. So I'm going to create a figure, and this figure is going to hold our color image, or I'll call it original, and we're going to do plot.imshow, and this is going to hold our image color. I can actually show you what happens otherwise if you want. Plot figure again, and then this is going to be our grayscale value. And it's going to be plot. I think I almost. What am I doing? Right. Okay. And then the last thing we always need to do is we just need to see it say plot.show. So we go back to our terminal and we execute our script, which was just seg.py. We should now get 2 images. Now we've done something funky here. I actually already know what it is, so let's go and fix that. I actually think we should close these down first though. Matplotlib. So let's go back to our script, and when we actually plot color grayscale image, we need to tell it that our color map space is grayscale, right? I think we do it like this. I don't think it needs to be all caps, that looks a bit aggressive. So let's try that again. And then we've got our grayscale image, and we've got our original image, which is great. So that's all working. So if we go back to our script now, we're going to move all of this down to the bottom, and we want to start doing our image segmentation now, our binary image segmentation on grayscale values. Now we're actually going to be looking at Otsu's algorithm and a triangle algorithm as well, so stick around. But essentially all binary segmentation is going to be is we're going to have some threshold value. So we're going to have a threshold, and we're basically going to say if our pixel is greater than this threshold value, then we're going to make that pixel some max value. So we're going to push it all the way to the 1 spectrum. Alternatively, otherwise, what we're going to do is we're going to say that pixel value, is going to be equal to 0. So that's some terrible pseudocode right there, but you kind of get what we're trying to do. So luckily, OpenCV actually allows us to do that. So we're going to define something. This is going to be we're going to have 2 values here. the return and thresh. So the return value is just the value that OpenCV chooses to be the best candidate to split our image into a foreground and a background, right? And then our threshold is going to hold our image, or thresh. So we're going to say CVT dot thresh. No, that's wrong. It's threshold. And then inside here we're going to give it our grayscale image. We don't want to give it our color image. And we're going to actually just define some arbitrary numbers. So this is our threshold value. So and then we're going to say it's 255. So right now every value that's greater than 0 we're saying is going to be pushed to 255. So if it's not black, it's white. That's what this statement is basically saying. If it's not black, it's white. Because black is 0 and 255 is white. So that's our threshold and that's our max value. So that's what we're doing. And then CV2 dot thresh, and there's a bunch of these. So you could also invert this, so do the opposite. We could look at that, but for now we're just going to do CV2 dot thresh binary. And I think we no longer really care about our original image. I think we all know what the image looks like. Actually, I shouldn't have done that. So what we're going to do is we're going to replace this with thresh. So this is going to just, I'm going to call this binary, and then this is going to hold our thresh value, and this should give us something. So let's execute our Python script. So again, what I haven't done is we haven't defined this color space, right? So I did this on the wrong one, but we still need to say cmap equals gray. What's going on here? So let's execute our Python script. So this is our binary. So we can see this is pretty terrible, because we can actually see that the only things that are really black are these outlines, you know, these little ridges all around the coin, and we can just about see those. So the algorithm is doing exactly what we've told it to do. If it's not black, then it's white, we've said. Now we could change these parameters a bit. So let's let's play around with that. So what happens if we say, well, actually only things greater than, say, 1 to 8 are going to be pushed to white, and everything else is going to be black. So what happens when we do that? So we get a completely different result now, and we can still see that within the coin, and this is what we were talking about earlier, there's a lot of white parts, but we can definitely see that where the coin has a lot of grey parts, more of it is now kind of distinguished between the background. We're not really done there yet, so this is really just binary. We're literally just saying, is this grayscale value bigger than this? If it is, then make it 255, otherwise make it 0. We can make those numbers anything. But we want to do something that's more interesting, so we're actually going to look at two different, but at least you know what's going on, at least you know the most fundamental way we can kind of segment an image. And if we actually chose a different image, for example, if we chose this colors, I wonder what would happen here. This might be more interesting. We can very distinctly see in binary, whatever the threshold is that we chose, it's clearly made everything 0. So everything was below that threshold. So that wasn't very useful. I want to go back to our coin though, because we're not done with that yet. Coins. So what we can do now is we're going to actually check out this Otsu calculation that we can do. And we do this by just adding it, and we say .otsu. And this is actually going to ignore these values, and it's just going to try and figure out itself. So what this Otsu threshold is going to do for us is going to try and determine single-handedly what the best threshold value is to split something into the foreground and into the background. So let's check that out. And we'll call that thresh2, and we'll now call that Otsu, and we'll call that thresh2. So let's execute our Python script again. So I made a mistake, and the reason is that we haven't actually said that this is part of the CV2 library. So it's cv2.thresh. So that's our initial grayscale value, and we can actually now see that this is what Otsu has done. And I can actually show you that, because if we change these values, if you remember what we got at the beginning, then this should now still be the same. See, so this is still the same, whereas before, when we did it with 0 and 255, all we had was this kind of outline, faint outline. So this algorithm has now done something. It's saying that this is the optimal value, and we can actually print this value. That'll be interesting. So let's say, what is this value that you think is so great? And the value is 170, so this is the grayscale value. So if we now actually implement it, if we just went back to our own program up here, and we set our threshold at 170, then although this is going to be really difficult to detect, what we should get is something that's completely identical to what that Otsu program, the Otsu algorithm, determined for us. So that's one thing. So we've done Otsu's algorithm, and by the way, what Otsu's algorithm does is it systematically kind of goes through your pixels, and it tries to push them. I think the way it describes it is it tries to maximize the interclass variance. So if you have a bunch of pixels that are sort of close together, it tries to push, it groups them and pushes them all towards 0 or towards 255, and it basically looks for the optimal way to push the most pixels in the opposite directions, if you will. So another one we can do, and I can actually show you the, whilst we're looking at thresh, I can show you what the inv does. So the inv, as you expect, it just does what we did before, except it's going to invert our value. So we've got a black background, and we've got white coins instead, and all the bits that were white are now black. So you can use that if you like. It makes no real difference. I don't really want it. So the last one we can do then is this triangle method, and from what I've actually played around with, this kind of seemed to work the best. I don't really I don't know what it's doing, so I can't describe that to you. But we're going to call that thresh 3, and what we can actually do, it'd be interesting to print the return value of that now. So let's print ret, and this is going to be thresh 3. So if we now execute this Python script, so our value is actually 252, which is really high. So all it's actually done, so this is actually probably the best one we've done, because remember what we're trying, we don't actually care about the coin. What we're just trying to say is what's part of the coin. So right now we could actually write a program that basically said, like with this one, with this triangle here, we could say any pixel which is 255 is part of the coin, and any pixel which is not 255 is not part of the coin. So if we actually look really close and we maximize this, we can only see a few small patches. So the next thing we could actually do is we could average all the pixels, right? So we could, with their neighbors. So what this would do is all of the pixels here should actually look at the surrounding areas, and they would say, well, that's black, that's black, that's black, maybe this should be black. So in this particular case that would work. It doesn't work in every case, of course, but it's pretty good. So this triangle method has actually given us the best solution to our problem currently. So what's now really interesting to say is, I think the value was 252, right? It's 252. So if we just show thresh again now, and we change our title once more to just binary, because these are all still binary thresholds, remember. And if we now execute our Python script one last time, then hopefully we get this really good result. And what we've basically done is we've basically said, unless it's actually white, we want it. We don't want it to. If it's actually white, then we want it to be white. Otherwise, it's going to be black. So we've really narrowed down the threshold. And what's interesting is to see what that background is. So I wonder what would happen if we made this. At what point does does this kind of fail. So let's make this 254. I kind of just like playing around to, you know, develop some intuition. So this is even better, arguably. So in our particular example, the best thing to do was to basically just say anything that's not 255 already, just make that 0. And that's actually given us a really good result. Again, I'm kind of rambling at this point, but I hope you've learned something, you've understood what's going on, you've been able to take something away from it. What's great, of course, is the code is pretty simple. You just need to install OpenCV if you haven't. Going forward, I'm going to be doing more thorough image segmentation. But I think this was a really nice example to build your intuition, that all we're doing is manipulating numbers, and one of the simplest ways we can do that is to say, well, we can choose some kind of pixel value, and if it's greater than that pixel value, then we want it to be one color, otherwise we want it to be another color. Now, of course, this only works when there's two things, really. That's why we talk about background and a foreground. The second you have like 5 or 6 different things, it doesn't make sense, right? It doesn't make sense because you can't have a lamppost being black and a road being black and a tree being black and then just the sky being white. You know, you're just kind of, you're overgeneralizing like massively. So we are going to have to use deep learning probably to get better methods, probably recurrent neural networks or convolutional neural networks. And if you're interested in that, then I definitely recommend subscribing. I am doing a lot of research. I've been watching the Stanford University lectures on computer vision, which are a really good resource. So yeah, if you're just interested in computer vision in general, what I'm trying to do with this channel basically is make computer vision more accessible. I think it has so many net positive applications. There are a few net applications of computer vision that I'm not fond of, not to make this political. But yeah, subscribe if you're interested in this topic, and leave a like and a comment, and thank you for watching.